Hello, my name is Juan Quintana. I'm a student at the University of Cincinnati. I work in the Microsystems and BioMEMS lab under the advising of Dr. Chong. And today I'll be presenting polysilicon thin film developed on ultra-thin flexible glass for temperature sensors. I hope you enjoy. Thank you for the opportunity to share my work. So in this project, we developed a polysilicon layer on ultra-thin flexible glass via aluminum-induced crystallization and fully characterized this material as a temperature sensor. The project is born from the need to track CVF on patients suffering from traumatic brain injury, so long-term damage is prevented. A device that can sustain within the body for extensive periods of time is desired, and we consider glass to be a suitable substrate as recent developments give it flexibility and ultra-thinness characteristics. Polysilicon is used as a sensing material due to its high TCR and thermal compatibility with glass. Hence, a developed polysilicon on ultra-thin flexible glass. Polysilicon was grown using aluminum-induced crystallization, or AIC, which consists of 3 steps. Deposition of 200 nanometers of aluminum on the glass and 202 nanometers of amorphous silicon on the aluminum. This difference in thickness ensures complete layer exchange during step 2. The sample is annealed at 400 degrees for 60 minutes with a 4 degrees Celsius per minute ramp rate. During this process, aluminum and amorphous silicon exchange places and a polysilicon crystalline layer doped by aluminum is developed on top of the glass substrate. In step 3, the exposed aluminum on top is removed by using an aluminum etchant, and afterwards, we started doing several tests to characterize the material's functionality as a temperature sensor. By doing an XRD, SEM, TLM test, we can characterize for crystallinity, grain size, and electrical response of the material. As we can see in the graph, we have peaks at 2 theta equal 28.5 degrees in the 111 direction and 47.5 degrees in the 220 direction. Confirming crystallization was successful, and by using the Scherrer relation, we calculated an average grain size of 21.6 nanometers. Then, by using a scanning electron microscope, we look at the grain sizes and agglomeration of the grains. By comparing it to previously developed polysilicon and polyimide, it's clear glass has a smaller and more agglomerate grain. This suggests higher thermal responses from the glass substrate developed material, as the last test will confirm. Transfer length method, or TLM, was used by placing an etched polysilicon strip on a probe station and measuring the resistance of different length to width ratios to calculate the sheet resistance. Finally, by sweeping the temperature from 30 to 45 degrees Celsius, we measured the thermal response of the material. Overall, polysilicon developed on glass shows higher sheet resistance and improved thermal sensitivity of 12% over its polyimide counterside. Interesting capabilities that can be applied in biomedicine. Thank you very much for your attention and your time. Have a good day.